Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our lecture series in thermodynamics. Today we look at incongruently melting compounds. Incongruently melting compounds. The term incongruent comes from the word congruent, which is a symmetry related term in mathematics. For example, when we say two things are congruent, when there are two images are congruent, for example, if we have A and B and we say they are congruent, what does that mean? It means you can translate this triangle into this other one. They look alike, so you can push this and it will overlap with this particular one. Those are said to be congruent. They are incongruent if, for example, you took a triangle and a rectangle. If you push this here to transpose it on this particular one, that will be the image which you get. It doesn't overlap. These are incongruent. So it's a symmetry, mathematical term associated with symmetry. So in the same way, when we talk of incongruently melting compounds, then it means if you have, for example, a compound A to B, it will not break down into A plus B as you're expecting an ideal situation. So let us look at that. How does it apply to eutectic systems, eutectic diagrams for selected systems, incongruently melting compounds? We are looking at the eutectic diagram. Now, let us take the example of sodium and potassium. Sodium and potassium. Sodium and potassium. So we have potassium, then we have sodium. And we have a compound, sodium 2K. This will be melting point of potassium, that will be of sodium. Now, when you do the freezing curves, you would have expected that the freezing curve is a compound. You would have expected that as you do the freezing curve, you would have probably theoretically expected, just like for the simple compound, that you will have that kind of a format. Where this one intersects at that particular point so that you have a eutectic mixture, this other one also at that particular point. Like we have seen in eutectic diagrams for compounds in the other lecture. But that is not correct. No. Big no. It doesn't overlap simply like that. What happens is very simple. What happens is very, very simple. This freezing curve intersects this curve outside the sodium matrix. So it intersects this curve at this particular point. And that is a peritectic point. Peritectic point. So first of all, let us label our segments here. One, we now know, if you have been going through our lectures, and I encourage you to look at those particular lectures. Here we now have potassium plus liquid. We have liquid. We have here sodium plus liquid. Here we have sodium compound plus sodium. Here we have sodium compound plus liquid. Here we have potassium plus sodium 2K. Now, let us assume now that we are increasing the temperature of this compound. It will move on according to that line. So we will start at that particular point. This is a eutectic point. Let's call it 1. Let's call that 1. And we are saying that we will have this particular point, let's call it M, let's call that P, and let's call that Q. So we are raising the temperature, we are increasing the temperature of the compound at state point M, and by the way, for these particular ones, this is about 280 K, that's about 273. For sodium, that's about it's slightly normally higher. That's about 371. That's about 371, and this is about 335. Okay. So that is for potassium. That is for sodium. They're in that range there. Now, at this particular point M, this we said is a peritectic point. At this particular point M, we'll have a peritectic reaction. We'll have a peritectic reaction or a phase reaction. Peritectic reaction. Also, we can call it a phase reaction. Remember, it's very important always to remember the difference. There is phase. We talked about phase rule. It's very, very important to distinguish that, because we have, in the biological sense, you have your phase. And then we have phase, which talks about solid, liquid, and gas. It's always good to remember that, because it's very easy for somebody to write, to mistake and write that as phase. That's biological. That has nothing to do with our physical systems. So here we talk of solid, liquid, and gas. Now, we have the peritectic reaction at state point M. At state point M. Now, what is the peritectic reaction? This peritectic reaction here, at state point M, we will have sodium, 2K, forming, that is solid, forming sodium, solid plus Al. Let's call that liquid to be represented by A. Let it be represented by A. The composition of that liquid be represented as A. Now, you notice once again here that the breakdown in terms of dissociation is not symmetrical. If it was symmetrical, this is incongruent. If it was congruent, we expected that if it was congruent, that is if and only if it was congruent, then we would have expected something like 2 sodium plus K. But that does not happen. So this is if it was congruent, that is. So it is incongruent. We are not getting that exactly what its chemical representation tells us when it dissociates. So, and then at this particular point, we have that liquid coexisting in equilibrium with this quantity at the state point M and that particular quantity there. So again now, because of phase rule, F is equals to C minus P plus 2. But remember, because pressure is constant, so if pressure is constant, this becomes 1. So the phase rule where pressure is constant is C minus P plus 1. So at this particular point, we have 2 components, 3 phases plus 1, and that would be 0. That would be 0. So it is invariant at that point. It doesn't change. The number of degrees of freedom is 0. So the temperature will be relatively constant here for some time. And then now, of course, as you continue increasing the temperature, now you're in this region where you have sodium and liquid. Remember, their relative amounts are given by the lever rule for the various segments. We have given lectures on lever principle, so you need to just go through it so that you are together. That gives you that the length of this segment represents the amount of liquid, and the length of this segment represents the amount of sodium in this quantity. And of course, at P finally, we have total fusion, total melting of this system, and so we have the liquid, or the homogeneous liquid there at that particular point. That's very, very important for us to note. Now, so that's a peritectic reaction. That's a peritectic reaction or a phase reaction. And it is an incongruent reaction because when the compound breaks down, it doesn't break down stoichiometrically into its component elements. It doesn't do that. Now, suppose we take an isopleth. Let's call it A, coming down this way. A, B, C, and D. And I believe now if you've been going through those lectures, simple eutectic diagrams, the lever principle, the phase rule, you are now able to interpret this is at your fingertips, so it should not be a big deal. So we know that at state point A, we have the liquid, at state point B, so let's just write down, so we don't assume, at state point A, we have the homogeneous liquid. As you continue lowering the temperature to state point B, we have the first crystals of sodium appearing, the first primary crystal. Of sodium appearing, and of course their relative amounts are given by Lever's rule. If I want to know the relative amount at this state point, let me call it B prime. I just draw that segment, this line here. Remember, we call this line a tie line. If you look at the Lever principle, that is called a tie line. So you just draw a tie line there. Now the length of this segment, let's call it x1 and x2. The ratio of those segments, that is x1, x2 over x1, is related to the number of moles. X1 will be representing moles of liquid. X1 is the number of moles of liquid. And X2 will be number of moles of sodium. That's the Lever principle. And so, as you continue moving down, we continue forming more and more of sodium and so forth. So at this particular point, state point C, again, remember, state point C, we have this liquid coexisting together with this mixture here and coexisting together with this particular mixture here. So we have three phases coexisting together in equilibrium, and again, based on phase rule, F will be 0, or the variance of the system is 0, or the system is invariant. So we expect temperature to be constant here. And then finally, when it starts dropping down, notice now there's no more liquid, we are just cooling the compound and the sodium. Now, what about if we are in the easy compartment? Let's take a state point here. Let's take a state point here, which let's say it is P. Let's call it L. Then at this particular point E. Then at this particular point F. At this particular point G. And then H. Again, now this is very, very simple for you. I believe it's simple for everyone. L, we're in the homogeneous liquid here. As when you come to E, we'll have the first crystals of potassium crystallizing out. The relative amounts can be gotten from the length of the segments at the state points. Just draw a tie line, and like you have said, using the Lever principle, you're able to tell the amounts, which relative amounts of potassium and the liquid. And of course, remember that the liquid composition is changing along the curve E1. That's the liquid composition. Liquid composition. It's the liquid curve. Now, at G, we have, remember, now we have the compound, we have the eutectic mixture, and we have the potassium. So the three are coexisting in equilibrium. So again, the system is invariant at that particular point. The system is invariant at that particular point. Just like we saw here, we had that coexisting together in equilibrium with this and that. Again, the system was invariant. Here also we now have this coexisting together with the eutectic mixture and the compound. So again, the temperature is constant. Then of course now when we start cooling down, the temperature is lowered. We are now forming this potassium and the compound. So basically we're just cooling potassium and the compounds. Very important for us to note. We have seen that we can have incongruent melting, and that is a phase or a peritectic reaction. It's a peritectic reaction. In other words, the compound does not dissociate symmetrically into its stoichiometric components. That's very, very important for us to know. And we have seen that we will apply always the lever principle and phase rule to be able to tell the relative amounts of the system in the system and to tell the characteristic features of the system, like for example, is it invariant or variant and so forth. So where we have the F as 0, we note that that system at that point, there will be a small halt in temperature drop for some time before it moves in whichever direction you are driving it. And very important also that you don't just apply the phase rule without knowing what you're talking about. If temperature and pressure is constant, then the phase rule is Fc minus P plus 1, where C is the component, P is the phases, and of course that represents temperature. If both temperature and pressure were constant, then the phase rule will simply be F is equal to C minus P if both temperature and pressure were constant. So that's very, very important to know what you, so you don't just use the phase rule and say it is F is equal to C minus P plus 2 and plug it in the system. Of course, it will not give you the correct interpretation of what is happening. So let us stop at that particular point. Thank you.